Assalamualaikum warahmatullahi wabarakatuh. Hi doctor, my name is Nurdana Adina Matino Akram and my number matrix is 227695. So today, me and my group consists of Tan Karhui and Ahmad Fahmi will present about the numerical analysis of corrosion and degradation in steel wire. Firstly, let's look at into the application overview. The numerical analysis of corrosion and degradation in industrial wire, including prediction and maintenance optimization app, is a MATLAB-based engineering tool developed to help the engineers and maintains the personnel and evaluate the corrosion behavior of high-strength steel wire quickly and accurately. The application predicts corrosion progression, estimate the remaining thickness of the steel wire, and support the maintenance planning using the numerical method. Next, the application integrates the least square linear regression to predict the corrosion growth from experimental data and the Newton-Raphson method to estimate the critical failure time and the Gordon succession method to determine the optimum maintenance schedule. Users can input the parameters such as initial wire thickness, applied stress, corrosion rate, and exposure time to perform the analysis. The application presents numerical results together with graphical visualization of corrosion progression and remaining thickness, enabling the users to assess the equipment condition and also estimate the service life and make informed the maintenance decision efficiently.
So I'll be explaining about the numerical methods used in this assignment. First of all is regression analysis. The objective of using this method is to forecast corrosion growth with extensive field testing. Uses least square linear regression to map corrosion depth over time. The next one is Newton-Raphson method. The objective for using this method is to determine remaining service life, solve the thickness equation iteratively to identify critical structural failure points. And lastly, we use golden section search method where the objective is to minimize the maintenance costs, balance repair costs versus failure risk to identify the most cost-effective schedule. The linear regression method is used to map the continuous corrosion depth profile DUT over discrete operational time measurements. A matrix-based least square approach is used. The Vandermonde matrix X and the observation vector Y are constructed from an experiment data pairs. The Newton-Raphson method was applied to compute the critical failure time, defined as the time at which residual ultimate load capacity equals the minimum allowable safety threshold. The nonlinear equation is shown in the slide, where T0 is the initial thickness, V is the baseline environmental corrosion rate, and Tc is the critical thickness. It was solved iteratively using the new Newton-Raphson update equation as shown in the slide and the difference Newton-Raphson equations. The iteration continues until conversion is achieved, yielding the critical failure time Tc, at which the residual ultimate load capacity matches the prescribed minimum safety threshold. The golden section search optimization was employed to determine the optimal maintenance time that minimizes the maintenance cost. Function Ft, the search interval ECAD 1 to 20 is iteratively reduced using the golden ratio equivalent to 0.61803 by evaluating the two interior points. We can use both the equation C for point C and D, and the interval containing the minimum is retained until the conversion criterion B minus A is less than 10 to the power of negative 5 is satisfied. The optimal maintenance time is then estimated as T equals to A plus B over 2, where with the minimum maintenance cost given by function F to the power of T.
Last but not least, the contribution to sustainability and planetary Earth based on our discussion. For the sustainability, the developed MATLAB application promote the sustainable industrial practice through the predictive maintenance by accurately predicting the corrosion progression and optimizing the maintenance schedule. This help extend the service life of high-strength steel wires and reduce the unnecessary component replacement and minimize the maintenance costs and improve the resource efficiency. The application also support SDG 9, which is Industry, Innovation and Infrastructure, and also SDG 12, which is Responsible Consumption and Production, by enhancing the infrastructure, reliability, and encourage the efficient use of materials. Lastly, the planetary Earth. By reducing the unnecessary maintenance activities and premature equipment replacement, the application helps minimize the industrial waste, conserve raw materials, and lower the energy consumption associated with manufacturing and maintenance process. Early prediction of corrosion also reduces the risk of equipment failure that could lead to the environmental pollution and safety hazards, contributing to a cleaner and safer environment while supporting long-term environmental sustainability.
Good day everyone. Today I will be demonstrating a MATLAB App Designer application designed for corrosion inspection and maintenance optimization. As we can see, the app interface is divided into several key sections. On the left, we have the inspection data panels, a show data button, and a main analysis button, run regression, find value, optimize. In the center, we have parameter panel where we can define our system initial properties like the wall thickness and the material stress, as well as environmental factor like the corrosion rate. The results are displayed here with a graph for regression analysis and a panel for final calculated results. Okay, the first step is to load our inspection data. So run. So it's to load our inspection data, and then we insert the data. So the thickness is 20, the wall diameter is 2, the stress is 5, the corrosion rate is 0.05. and environmental we choose acidic, and the thickness we can choose 8, and then we choose the cost weight, and then run regression. This is the graph, and then we can find the failure time and optimize. So we can figure out the optimal maintenance, which is 10 years, and the minimum cost is 200 ringgit. So this calculate the corrosion analysis. So the code behind the button solve a non-linear equation for time using a Newton-Raphson method. This equation model the corrosion depth and compare it to the critical thickness until it find the exact failure time. The results is then displayed in the result panels. Finally, the optimize button define a cost function. Use a powerful algorithm to determine the optimal maintenance schedule. This is a crucial step that balances the cost and risk. The callback function for this button defines a cost function that accounts for maintenance cost and the risk of failure. It then used the golden section search method, a robust one-dimensional optimization technique to find the minimum of the function. This provides us with the exact time for maintenance and the associated minimum cost, as shown here. So this application demonstrates a comprehensive workflow for corrosion engineers. By integrating data analysis with advanced numerical method, we can accurately predict failure time and, most importantly, optimize maintenance schedules to minimize costs and ensure safety.